Hello everyone. So today I will show you the eddy current array using lift-off compensation technology. This way to use eddy current is a very good advantage compared to magnetic particle and penetrant inspection methods on some in some case it's a good replacement. So we're gonna see that in this presentation. So the agenda. So common industry challenges, eddy current array solution, the lift-off compensation technology, and the result of MagnaFORM, and the depth sizing result. And at the end, I will make a real-time demo. So common industry challenges. So you know, in the field, the weather is always different. So sometimes it's you have rain, sometimes it's really hot or really cold. So this kind of situation about the weather can be a big challenge for some legacy NDT methods. Another cause of challenge is the surface condition. So sometimes we have corrosion, sometimes we have sandblasted surface, or sometimes we have rough wells, so non-flush well or well with multiple passes. On top of that, sometimes we have we have something on the surface like paint or even grease or dust, any kind of dirt. So the legacy NDT methods are affected by this kind of condition. So we have to deal with it if we have to work outside. So the MT and PT are really affected by that. Sometimes you have to, it can cause delay or sometimes lack of detection, and surface condition, again, you can have false indication and lack of detection, and dirt and paint is most of the time a big issue for that type of inspection, especially for PT, where the surface needs to be extra clean. Eddy current array solution. So the eddy current is not affected by bad weather condition. So even if you have water on the surface, you have paint, you have dirt, eddy current will work. The only thing affecting eddy current is if you have kind of example ferromagnetic paint on top. So, but most of the time it's not happening. So all the bad weather condition or surface condition is not a problem for eddy current technology. So if we go back to the beginning, so rain is not affecting eddy current. Eddy current probe can be used on hot surface up to 85 degrees Celsius. On top of that, we have new wedge now, and the wedge is good up to 160 degrees Celsius. And the cold surface as well is not affected eddy current. So even if the part is really hot or really cold, you can balance on the part outside, and that's going to work. So eddy current on corroded surfaces. So the advantage of eddy current on corroded surfaces eliminate noise caused by corrosion. So as you can see here, we have a corroded surface and we don't have any noise. And we can see the three ADM notch. In this case, no filters are required. So that means we don't have to spend time to analyze the data after, you can see the results in the real time. So the POD is extremely high. So again, the analysis is not, you don't have to spend time to make analysis, and depth sizing is possible. Eddy current on sun-blasted surface. So sun-blasted surface is really rough for probe when you have to keep a good contact with the part. So the new MagnaFORM wear protection was tested on 22 kilometer scan. So no Teflon tape are required. The contact is not required. So that means if you don't have any contact, the 22 kilometers can be stretched to a very high limit because there's no contact. And the probe is easy to slide on rough surfaces. It's really important when you have to work hours and hours with eddy current probe, and you have to press the probe on the part and to keep a good contact and move it. It's really hard on arm and shoulders. So this new technology, you can move the probe with one finger. So it's easy to move. So the eddy current array solution. So what is the lift-off compensation technology? So the MagnaFORM solution. So it's a new way to perform eddy current array. I'm going to show you how it works. So basically, we use the same instrument with a dedicated software. So the MagnaFORM solution, so we use the same OmniScan MX. So the MX1 now, we have a new part number, and now the instrument is compliant with CE and ROSE compliance. And last revision was 2018. And then the MXC Well 1.0R6 software was, the last revision was launched in September 2019. So the MagnaFORM probe, we have designed this probe to be rugged. So we have a new detachable connector. We can change a pre-shaped wedge, and the sensitive face is a PCB. So I'm going to show you how it works. So tool-free removable wedges, so you can change the wedges easily. On the number 2, you can see the wear protection, and the yellow PCB is under the protection as well. And you can slide out, and number 4, you can slide out the wedge. We have developed different wedges to fit most pipes and vessels, but in fact, we can have so many different type of wedges. These ones were developed for weld. So the new PCB. So we have 16 plus 16 sensors. So we have 2 types of sensors for the total of 32 coils. The active circuitry means in this probe, we have the multiplexer in the probe. So we don't use the multiplexer in the instrument. We have a lot of advantage doing this. Example, we have a 5-meter cable, and we don't have any problem with noise. So the type 1 is a crack detector. So, and the type 2 is a lift-off gauge. So that's we have 2 types of coils. So I'm going to show you on the next slide what we can do with that. So type 1, the PCB equivalent to cross-wound coil. Cross-wound coil is the coil used in the well probe for decades. So it's very good for carbon steel. It's not really sensitive to permeability change. That's the reason why this probe is used for a long time in the well industry. This probe can detect easily surface breaking defect, but if you use a Nortec 600 with regular well probe, this kind of probe is affected by liftoff and pain as well. So the type 2 sensor is a liftoff gauge. So it's a PCB version of sliding probe. Sliding probe is a probe used again for decades in aerospace industry to detect cracks, subsurface crack between rivets. So it's the reason why we use that. It's a very stable liftoff measurement with that type of coils. So the powerful combination. So it's almost magic. So we, at the end, we will have a dynamic liftoff compensation. How it works? We have 16 independent crack detectors in the PCB. We have 16 liftoff gauges, and the result is a 16 independent dynamic liftoff compensated channels. So yeah, the PCB is flexible, but even if the PCB is flexible, it's impossible to match a well profile or corrosion, or you always have different liftoff, and it's really hard to keep the same distance between all coils and the part. So how the liftoff compensation works. So as you can see, even if the probe is flexible, we have different liftoff case, and the raw signal is affected by that. With the compensated crack signal, the signal is all the same even if the liftoff change. So we have a short video showing the how it works. So you can see the signal on screen without liftoff. So that means the part is in contact with the probe is in contact with the part. So after 3 millimeters of liftoff, as you can see, we have the same result. That means if you, example, you have a painted surface and you have 1, 2, 3 millimeters of paint, the signal is always the same. So that makes the inspection really easy, and the POD is extremely high, because you can miss a defect even if the coil is not in good contact. On top of it, if you want to prevent damage on the part or prevent damage on the probes itself, you can lift the probe by 1 or 2 millimeters and just fly over the part. So the MagnaFORM result on lift. So here we have a pipe. So it's painted pipes. As you can see, the weld is about 1 inch wide, and we have different crack in the heat affected zone on top of the weld. So in this case, the challenge was to make a setup without any filters. So when you don't use filters, even if you have a 2-inch long cracks, you will see the all crack on the screen. So the problem when using filters is you will you will see, for longitudinal crack, you will see the beginning of the crack and the end of the crack. All the middle of the crack will not be there. So you will have to make analysis at the end to see if you have too small crack or a long crack. But with the MagnaFORM, you will see exactly you will see the whole length of the defect on the screen. So as you can see, even if the cable is 5 meters long, even if you have this kind of surface and the surface is painted, you don't have any noise. It's clean. So the permeability change again. So in this case, we have the bare metal, we have the heat affected zone, and we have the well. So we have 3 different permeabilities. But as you can see on the screen, we can see that. So the cross one coil is making a great job on it too. Okay, so the result is a very high POD. So even if you scan the part 100 times or for 8 hours, first you don't have to press null. You don't have to press null because the 16 lift-off gauge are measuring the lift-off in the real time. So if you scan for 8 hours, the 16 code is working for you for 8 hours. So the null is not required. So time after time after time, the screen is the result on the screen is the same. So the analysis is not really required. What you have to do, you find indication, you press save, and then you save the data. And on top of that, the depth sizing is also possible. Okay, this one is really, really interesting. I don't know if you know that type of stainless steel alloys, 300 series, like 304, 316, 347. It's really popular, okay? It's not ferromagnetic, so MT is not working. Only PT work on it. So imagine if you have a very nice part in, on the lab, easy to do. Outside, if you have to use PT to inspect stainless steel, that means you have to deal with the rain, the cold weather, hot weather, rough surface, painted sometime, dirt on it. It's a big challenge for PT, and PT takes time. PT outside, you have to apply your penetrant, and you have to respect the dwell time on the procedures, and then you have to wash. Imagine if you have to wash a corroded surface, because you can have stainless steel corroded in some case, or if it's dirt, it's a big job, because penetrant is penetrant. So you have to wash and wash. And then after that, you have to apply your developer, and then you have again a dwell time, okay? And then you will have a ton of false indication, and you have to wipe it off and wait to see if the penetrant is going out of the crack. So it takes time. And when you have a large area, it's a big challenge. When we have to use eddy current on it, it's another challenge. It's another type of challenge, but it's still a big challenge for eddy current. Why? Because on this type of stainless steel, even if you change your frequency, and even if you use filters, there's nothing to do. Your lift-off signal and your crack signal have about the same phase. So that means if the coil is not in good contact with the part, your signal of the lift-off is right on the crack signal. So you will have a ton a false indication with eddy current normally, even if you use ECT or ECA. But as you can see on the screen with the MagnaFORM, we don't have noise. And I'm going to explain you why. In this case, we have a set of coil measuring the liftoff in a real time. So that makes a huge difference. As you can see here, it's almost unbelievable, but in this case, we have a flat bottom hole of 1.6 millimeter. So it's about 1/16 of an inch, okay? Again, we have a transversal notch, same length. We have a 45-degree, and we have a longitudinal notch. So in this case, I use two-color palette, red and blue, to make the difference between the transversal defect and the longitudinal. So positive signal is red, negative signal is blue. So as you can see on the plate, we're talking about very, very small cracks. What is interesting on that is, even if you know, on the left-hand side, we don't have any liftoff, 0 millimeter of liftoff. On the right-hand side, we have 3 millimeter of liftoff. So almost, the liftoff is almost the double of the size of the crack, okay? And look, it's the same, okay? So that means if you are working outside in the field and your probe is not in a perfect contact, you will have this kind of result, you know, no noise. And even if you scan the part for 8 hours, again, you don't have to null. And the 16 liftoff gauge will make the job for you for hours and hours. So we have the result on the same type of alloys, as you can see on the plate. Okay. So what is interesting on that one, that plate was, the surface finish was different. So we have some grinded section, some rough section, and as you can see, again, we don't have any noise. So the signal that we have is, as you can see on, if I go back here, you see we have a very high POD to detect a 1.6 millimeter crack in different orientation, like transversal and longitudinal, and even pitting, like in this case, flat bottom hole is to make to simulate a pit, you know, of 1.6. But what happened when we have stress corrosion cracking? So stress corrosion cracking is a lot of little pitting, and the crack is link all the pit together. So we have a colony of crack in one area. So as you can see before, we have one crack, we can detect it. We have a colony of crack, yes, we can detect it again. Why we have a so large signal, even if we have maybe 200 cracks, is the reason is the coil have a certain size, and when the coil touch a crack and touch another crack in the same time, but the signal is linked together, you know. So that's the reason why we have this kind of indication. But the thing is, the first goal is to detect. So can we detect small crack? Yes. Can we detect colony of crack? Yes. Do we have noise caused by surface condition around and liftoff signal? No. As you can see, the result is really clean. This one is interesting We have a part with 3 millimeter Inconel cladding. We have Inconel weld, and we have long crack in the roots of weld, So again, we don't have noise caused by this kind of surface. We can see the entire length of the defect. Even you can change the length of scan as well, so you can work with in the real time and have a 2 feet long crack, and then you have to stretch your scan as well, but still you can detect crack in Inconel alloys too. Depth sizing. So depth sizing is a very big goal right now because it's not really possible with MT and PT. With eddy current, we can detect the depth of flat bottom hole to simulate pitting, and also we can detect the depth of crack. It also worked well on duplex stainless steel. Before the pandemic, I made tests on it, and the result was very good, on duplex stainless steel, and carbon steel. So lift-off compensation helped to get a reliable depth sizing evaluation on carbon steel, yeah, for sure. But for weld, corroded surface, painted surface, stress corrosion cracking, it works. I'm going to show you in the next slide. So that depth sizing on welds. As you can see before, it's not possible to match exactly the profile of the weld everywhere, especially when you have a long weld to inspect. So if you have different depth, the amplitude of signal will change. But if you have lift-off, the amplitude of signal will change too. So in this case, we can figure the 3 millimeter depth crack with lift-off the amplitude of signal will look like a 1 millimeter deep crack without lift-off. So it can cause confusion when you have a rough surface when the lift-off change, So in this case, the signal, when the signal is dynamically compensated, you have the same amplitude of signal than the 3 millimeter without lift-off. That's what we want. So what happened when we have a crack in the corrosion pit, like what we can see here on the corroded surface? We have 3 notches. So we don't want to know the depth of crack from the surface. We want to know the real depth of crack. So when using lift-off compensation technology, you can try that. Only the crack depth will be recorded. In this case, as you can see here, we have the 3 millimeter depth of crack. So you can see on the impedance plane the amplitude of signal, and on the strip chart you can see the crack signal on the strip chart. So imagine if we have paint on it. Another challenge on top of the challenge. So we have a profile of well, you know, with different shapes and different distance with the coil, and on top of it we had a coat of paint. So what's going to happen? So on carbon steel, normally you can go up to 5 millimeter and have the same result. So imagine if you have here, you have maybe 2 millimeter of paint on top of it. So maybe at the beginning you had a lift off of 1 millimeters, but it can be now 3 millimeters with paint, but it's okay. The result will be the same. So you can go up to 5 millimeter paint thickness. So from the coil to the top of the crack, if you have 5 millimeter and less, the amplitude of signal will be the same. So the advantage is you don't have to measure the thickness of the paint. It's not an issue. You don't have to do that. Normally, when we have to use well probe on the Nortec in the kit, we have a probe to measure the paint thickness. But in this case, the lift-off gauge will make the job because paint or air is the same. So what's happened when we have crack colony? So stress corrosion cracking can happen in stainless steel and in carbon steel as well, you know. So if we have this kind of result, you want to know the deepest crack, because the deepest crack will the crack you will use in your report to accept or reject, depending the procedure you have to follow. With the MagnaFORM, we can see on the strip chart here, the depth reading will be always the deepest one. In this case, the deepest one is right here. So if my procedure says reject all crack of 2 millimeters and higher, it's acceptable. But if the procedure says you have to reject all crack over 1 millimeter deep, then you have to reject it. So what is important? Always the deepest crack is recorded. So the conclusion, here we have stress corrosion cracking on steel. So as you can see, we have multiple crack. So this is the kind of image of stress corrosion cracking. Result on corroded pipe. So I'm going to switch my screen. So the result on corroded pipe, so I have an omniscan here, and I have a corroded piece of pipeline. And as you can see here, I'm going to scan, test one, I'm going to scan the crack to detect the crack transversal to the probe. Test two, I will scan on that direction again. So the crack will be longitudinal to the probe. And on top of it, I will add a row of papers, okay, on top of the pipe, and we'll see the result. For that test, the crack are pretty close, so I will use a 1-to-1 ratio scan, so to see all the crack in the same screen. So what I have to do, I put the probe on my part, so I don't have to press null. Okay, even if I scan the part today and tomorrow I restart the instrument, what I have to do, the instrument will only we will have a message on the screen and pop-up message saying leave the probe in the air and press OK. That's it, and then you're ready to go. So that's what I'm gonna do. I'm gonna switch my screen. Freeze. So now mouse. So now I can use that cursor here to measure the length. So the length is about 12 millimeters long. So I can measure different angle or longitudinal. So this is the X and Y measurement. Then if I want to make a report, I can see on the impedance plane, I can see the amplitude of signal. I can see the depth of the crack here. And on the strip chart, I can see the crack. So if I want to stretch, so now we have three different different crack depths. So in this case, we can see the three crack on the strip chart, and on the impedance plane, the three signal are there, but it's, we have exactly the same angle. Okay. So if I unfreeze and I turn the probe by 90 degrees, and scan again, we have we can see the crack here is longitudinal crack. So you see the length is the same, and the signal is negative now because we have cross-wound coil, and cross-wound coil is sensitive to the orientation of defect. So that's the reason why when we use two different color palette, we can know the orientation of the crack. So again, so you see the depth here. Even if you measure the crack in transversal or longitudinal, the depth reading is the same. So now, what happened when I'm gonna unfreeze. I'm gonna put a book on top of my parts. In fact, I'm doing the same than the video you have seen before. So I had about 3 millimeter of liftoff, and then I scan on the paper to simulate paint or liftoff, you know. So I'm going to scan again. Make sure I have everything on my screen. Bam. So you remember the result we had before. Yeah, the problem is I can reach the middle of the crack, but I had to scan again to be in the middle. But normally the depth sizing is working with the liftoff. So normally you can have 10 to 20% off when you have to deal with liftoff, but still it's a pretty good result on to measure the depth of crack. So if I go back here, so the conclusion, so eddy current with the lift-off compensation technology is a good option to replace magnetic particle and penetrant inspection when you have some condition. Okay, MT and PT are really good NDT methods, and they have their advantages. You know, example when you have a batch to do, or you know, but in some case, especially in the field, the eddy current array with the lift-off compensation can be a very good option to save time. We don't have to use any chemicals. If you want, you can clean. The cleaning is not mandatory. If you make your setup at the beginning and you calibrate on your plate at the same temperature, then the part you have to inspect, there's no problem. Okay, so most of the time the part are sunblasted for any reason. Sunblasted surface is a big challenge for MT, PT, eddy current. It's really rough. It's like sandpaper. Okay, and if you want to use penetrant on sandpaper, it's really hard to wipe. And if you try to use powder with a magnetic yoke, it's not so easy again, you know. So this new technology is the new way of Olympus to make probe, you know, PCB lift-off compensation. So we have a lot of advantage. So the good thing is carbon steel, stainless steel, Inconel, you can add duplex stainless steel, can be inspected with the same probe. On top of it, if you have to inspect stainless steel, 304, 316, you can use the same setup. You don't have to change the setup. The setup will work even if you change the alloy grade, you know. Depth sizing can be made on rough, welded, and printed surface. It's really important. Right now in the industry, there's a big wish for to get depth sizing. So we are with eddy current array with lift-off compensation. We are a really good position to achieve this kind of goal.